And here we go. This is going to be chapter 13.1 and chapter 14 for covering gas laws. And we're going to start with the nature of gases. And we're going to start with air is a gas mixture. It's a mixture of a whole bunch of other gases. 78% of it is actually nitrogen. 21% of it is oxygen, and 1% is a whole bunch of other stuff, carbon dioxide and all the noble gases and that sort of thing. Carbon dioxide is actually remarkably non-abundant, relatively rare, considering how much plant life we have on the planet. And if there was more carbon dioxide, the plants would go nutso with all of the food that they're getting. Now, the properties of gases. Most gases are colorless and invisible, with a few exceptions. Chlorine is yellow, and nitrogen dioxide is a reddish brown. Gases fill the container they are placed in. Not just take the shape, but they also expand to fill the container. And some gases exist as atoms, for example, the noble gases. There are 7 that exist as diatomics, and hopefully you remember those. Those are the H2, N2, O2, F2, Cl2, Br2, and I2. We, of course, refer to these as the Magnificent Seven, and those are our 7 diatomics. And then there are other gases that are molecular compounds like CH4 or CO2 or let's see what others are there. NH3 can be a gas, and so on. Okay, gases are compressible, which means that's why they're used in shock absorbers and airbags for cars, or even paintball guns and those little CO2 cartridges, or propane, tanks and that sort of thing. Gases diffuse. They can move through each other rapidly. This is why when we have a spigot in the classroom, a gas spigot open, and I have the gas on, you guys come into my classroom and complain, "Ooh, it smells like gas in here." Well, how did it smell like gas? Because it only came from one spigot. So that smell permeates through the class pretty quickly. It is also how when a disgusting person decides to light one off in class, you get to catch a whiff of their lovely aroma so quickly, because the particles travel through class very quickly. Okay, gases exert pressure on the walls of their containers. Pressure is equal to the force times divided by the area of the wall that they're touching. And the basic unit for it is a Pascal, which is 1 Newton per meter. It's roughly the weight of a baseball spread across the table. It's not very much. Okay, the pressure of the gas depends on its temperature. Okay, and higher temperatures exert greater pressures. Okay, and all this is explained through what's called the kinetic molecular theory, and all the gas properties are explained using this model. I realized I dropped a little too low. Okay, the theory is developed primarily by the 3 scientists taking over 100 years to develop. Rudolf Clausius, James Maxwell, and Ludwig Boltzmann. Okay, which brings us to the components of the kinetic molecular theory. The first one is gases consist of tiny particles with mass. Okay, they have mass, but they're very, very small. Okay, the particles of gas are separated each other by large distances, and the volume of the gas particle itself is considered negligible. In other words, the actual size of the particle doesn't matter, but what does matter is that volume is a function of the distance between the molecules. Not the size of the molecule, not the size of the particle. All right, so volume is a function of the distance between the molecules, not the size of the particle. All right, now gas particles are in constant rapid random motion. For example, hydrogen travels at about a mile per second, which can be extrapolated to 3,600 miles per hour, or roughly 5.5 times the speed of sound. Quite fast. Okay. Collisions of gas particles with each other or the walls of the container are perfectly elastic, so no energy is lost. In class, when we do the, you'll witness the happy ball and sad ball demo, and elastic collisions happen when the happy ball bounces, and inelastic collisions happen when the sad ball bounces or doesn't bounce, for that matter. Okay. Temperature, then, is a measure of the average kinetic energy of the gas particles. It is given by Ke equals 1/2 of the mass times the velocity squared. And higher temperatures have a higher kinetic energy, and vice versa. So, the example of this is right here. And this is a distribution of molecular kinetic energy. Here's how it works. The cold graph is the blue graph is the cold temperature of water, and the red graph is high temperature water. And the vertical, this vertical line here, let's make this a little darker. This vertical line would be the average kinetic energy of the cold temperature water, and this would be the average kinetic energy of the hot temperature water, and it's right at the peak of the curves. Okay, and it is always the peak of the curves just because we have so many, we're counting so many particles here that it's always going to be the peak of the curve. Now, there is overlap, and notice that these particles right here, let's make it a little like that. Oh, that's not what I wanted. I don't want those. That this range right in here, okay, for the cool temperature particles is, let's draw this line again. This line in here, this is the temperature of the high temperature. This is the average high temperature particle. But notice that there are some cold temperature particles that have this kinetic energy. There's just a lot fewer, and the average kinetic energy is way over here. Now, that means it's for this purpose. Or, for example, let's say that this point right here is, let's say that that's the boiling point. That means that all of these molecules over here, okay, are, right, all of these molecules over here have enough kinetic energy to boil, right? Well, that also means that these guys down here of the cold temperature also have enough kinetic energy as individuals to escape and evaporate from their liquid. And here's the rest of them that don't have the kinetic energy to do it. And so this is why you can set out a glass of water, and it will begin to evaporate even though it's not boiling at all. Those few particles will start escaping, and it'll create less and less. And what this actually does is it moves the average temperature of this. It starts moving. Oh, that's not what I want. I want that one to move. It starts moving this temperature this way because we start losing the temperature, the energy of the high temperature molecules. And that's why evaporative cooling works, is because when the particles evaporate from a liquid, it actually creates, it actually lowers the temperature of the remaining liquid. And that's why sweating is so effective on humans. We get the liquid to evaporate from our body, and our body temperature goes down because we're losing some of the kinetic energy of the molecules. Okay, so we'll flip to the next page here in just a moment. All right, this brings us to the last part of the KMT, and that's gas particles exert no force on each other. The dispersion forces and the dipole-dipole forces, back in chapter 8, I believe, talked about how molecules would be attracted to each other if they're very close, and they have this random positive and negative ends to each other, and so they'll have this slight attraction. Well, the KMT assumes that does not exist. And it needs to do that because the molecules are traveling fast enough due to random motion, and frankly for the models to work. Even though we know it does exist, and when things get really, really cold, the KMT tends to break down. Okay. Now there's 4 primary variables that can change in the behavior of gases. And the first one is the amount of the gas, which is given in moles, or N. In physics, it is often given as capital N. I want to change the color of that. It's often given as capital N. Okay, but this equals the exact number of particles. So we take this big number n and we divide it by the little number n, and we should get ... That's right, 6 times 10 to the 23rd, hashtag mind blown. Okay, this total number of particles divided by the number of moles would then be 6.02 times 10 to the 23rd. But you guys knew that. Okay, that brings us to, N also equals the mass divided by the molar mass, which should also make sense, that if N is the number of moles, and we divide the total mass we have by the molar mass, that's going to give us the number of moles. All right. Our volume is given by V. This is always in the units of liters. We have a temperature, which is T, and this is in the absolute temperature scale, which is in Kelvin, and it must be used in all gas law problems. This is because Kelvin sets 0 kinetic energy equal to 0 temperature, and for us to do all of our calculations, they must all be proportional and include a level of 0. Fahrenheit and Celsius both have negative values, and when you incorporate negative values into proportions, things get all wonky. To convert to Kelvin from Celsius, we use this simple one. Kelvin equals Celsius plus 273 degrees. Or we can use the Fahrenheit one, which is Kelvin equals 1.8 times the Fahrenheit temperature plus 459. And then finally we have pressure, which is P. Now gas pressure is an interesting property. Our atmosphere is made of many gases. It's about 60 miles thick. And the force of gravity from all of this gas exerts a pressure of 1 atmosphere at 0 degrees Celsius on a clear day at sea level. So imagine you're at the coast sitting on the beach, and it's very cold, and it is freezing cold, and the air pressure that you're experiencing at that time is 1 atmosphere. Okay. We use a barometer to measure this. Okay, and barometers use mercury, and you may have heard of this before, to measure the pressure. Okay, here's our barometer, and what this does is we have the pressure of the air pushing down on a pool of mercury. And the greater the pressure, the more mercury gets sent up into the tube, and the higher a column of mercury is supported. And so as we go to a lower temperature, a lower pressure area, like say the top of Mount Everest, there is less pressure shooting the mercury back up the tube, or supporting a column of mercury that is only 253 millimeters high, as opposed to normal barometric pressure, which is 760 millimeters high. Okay, so this is why it is so flippin' hard for people to climb Mount Everest, because the air pressure is 1/3 of the pressure that is in 1/3 of the pressure that is in that's at sea level. And so we have to work so much hard, 3 times as hard, to get the same amount of oxygen into our breath. And that's why people die, because they have to be in amazing physical shape just to get up there, and they're getting less and less air as they do it. Okay, now mercury is used instead of water in this case because mercury is very heavy, and it is 200 grams per mole, and water is only 18 grams per mole. And so you can imagine that for the same volume of material, it's going to require significantly fewer atoms of mercury than it will water. And that's why we use mercury instead of water. However, it's quite poisonous, and so we don't want to touch it a whole lot. Okay, now, there are various conversions for this. 1 atmosphere has a number of other... pressure has been redefined in a number of different ways. And we've discovered a number of different ways and found out that they're really similar, or that they're all the same. They just have we've used different units for different purposes because we need to use them differently. So 1 atmosphere equals 101,325 pascals. We talked about the pascal being the baseball on the coffee table. But that's a really unwieldy number. It's really big, and we deal with a lot of pascals and large pressure changes. And because of that, we shift to the kilopascal. And so this amount is a 101.3 kilopascals, or 101.3 thousand pascals. But then again, we also have people that deal with English units. And so we're talking about 14.7 pounds per square inch, which we try to get away from in here, but you'll still see instances of English units being used in outside of the world. Okay. Then there is 760 millimeters of mercury, and that's the height of the column that was being held up, or 76 centimeters of mercury, 3/4 of a meter. And that amount is the same as 29.9 inches of mercury. Again, English units, boo, we don't like those. Okay. Now, this 760 millimeters of mercury was discovered by Alessandro Torricelli, and so we renamed this unit, the millimeters of mercury, we renamed it Torr. Please forgive my sniffles, I do have a bit of a cold. Okay, so 760 torr, the unit was named for Torricelli, and they took the millimeters of mercury. 100,000 pascals is 1 bar, and so it is a large metric unit, and meteorologists use this. And 1 bar is slightly less than 1 atmosphere, but they're pretty darn close. Now, these values can be used as conversion factors. And so, a couple of examples. If we start with 460 millimeters of mercury, okay, we want to convert it to how many pascals? Not kilopascals, just pascals. And if we have 460 millimeters of mercury, well, we know that 1 atmosphere equals 760 millimeters of mercury. And so we can convert to atmospheres. And we also know that 1 atmosphere is equal to 101,325 pascals. And so we can convert to that. And that's going to wind us up with 61,328 pascals. And so that's that conversion. But notice here that 1 atmosphere equals 1 atmosphere. So we can actually jump the atmosphere part and go straight to the units of the other pressure that equal 1 atmosphere. So if we're going to convert, say, 25 pounds per square inch into inches of mercury, and this should be a superscript right there. And that's going to be 25 pounds per square inch times, well, we know that 14.7 pounds per square inch is, I'm getting a little low here. Let's readjust. There we go. We know the 14.7 pounds per square inch from right here is equal to 1 atmosphere. And so we can, where's my select? There's my selector. And so we can set the 14.7 pounds per square inch equal to 29.9 inches of mercury, and we're left with 50.9 inches of mercury as the conversion. All right, that will do it for 13.1, and we'll see you guys next time for 14.1 and the rest of Chapter 14. And this is P-Dog signing off.